Okay, so section 3.1, rates of change, talking about calculus. We've watched a video on YouTube, Newton versus Leibniz, calculus controversy, look it up. Okay, so here we go. Average rate before calculus. Jezreel, say once again how we solve for average rate.
Subtract 2 points.
Subtract 2 points? Oh. That's just going to be a change in y. That doesn't mean anything. How do we find an average rate of change? Add them all up.
I thought I was wrong. I was just saying.
We just said it a second ago. What do we solve for? Slope. Okay, so what's the formula for slope?
M equals y2 minus y2 minus x. Change in y.
Okay, so that is the formula for slope, but technically we're talking about average rate. So an application of slope. Can someone give me like a very, very, very common measurement of rate? Miles per hour. That's a good one because change in miles over change in hours, which means you need time to pass. Then you can measure a distance, and then you say, on average, over this time interval, how fast were you going? Average rate uses 2 points. Now, my physics people, you know that in physics that we don't usually use x's in word problems for the independent variable. What do we use? T, standing for time. So therefore, if I was to change it from x's to time, I could do time 2 minus time 1, and I could take whatever function, whatever movement is happening, and take y2 minus y1. But question, do they actually have to give me the y's, or if they give me a function, can I just plug in the x's and solve? Yeah, if they give me the function, I'm good. So average rate is just a slope formula, but applied, almost always applied. Now, with average rate, a way of describing it could be, I'll put it this way. Rate of f of x, but if we're doing like physics applications, it'll be f of t. Here's verbiage or words that you're going to see very often. My boys, shush, you're distracting me. The rate of f of t over, it's always going to have an over because there is going to be a passage of time, as I was saying earlier. And guys, what kind of notation am I using to show that passage of time? Doesn't mean every problem's going to have it, but there's some time passing. So from t1 to t2, because I have to have 2 points to find a slope, right? Now, graphically, what is that going to look like? Well, if I have a graph of a parabola. Now, hold on. Wait. Slope. What did you always find slope of? Lines. And why were we always finding slopes of lines?
So you can plug it in to the equation.
No, like ever since algebra 1, why were we only finding slopes of lines? Because they're constant. They're going to have the same slope everywhere. I can pick any 2 points and find change in y over change in x, and it's the same. Last year, did we talk about a section where we were finding the slopes of a quadratic? Slopes of a tangent line. Yes, but it was horrible. It was messy, and then we basically were like, yay, let's do 1 or 2, done. However, question. First of all, does all motion work in or model after a linear pattern? No. Does all motion pattern or model after a parabolic motion or parabolic pattern? No. So I just have like a random example I came up with off the top of my head. However, motion can happen in lots of different patterns, lots of different paths, right? Okay, if I was to take 2 random times, because it's over a time interval, right? From some t1 to some t2, there has to be a passage of time. I could, if I knew my function, plug in and get my f of t2, right? And I could plug my t2 in, sorry, f of t1, I lost track of which point I was at. Then f of t2, I could plug in and get my f of t2. If I was finding the slope, I wouldn't be finding the slope of the quadratic. I'd be finding the slope through the quadratic. And what is a line that goes through a graph? In more than 1 point. A secant line. And that's something that we learned in geometry. Didn't you learn about secant lines in geometry? But they were secant lines through what?
A circle.
Only circles. However, once again, is motion only patterning after a circular? No. So secant lines can apply to anything. In a sense of, to any type of motion, any type of curve. It's just a line that goes through, in a specific region, goes through 2 points. Now, guys, could this randomly, take a turn and it's up here like a roller coaster? And could the secant line maybe hit somewhere else?
Mm-hmm.
Yeah. But what I'm talking about is this region right here from T1 to T2. I don't care if way over in Timbuktu somewhere it hits again. It's still a secant line if it crosses through a graph. Okay. So average rate graphically can be described as the slope of a secant line. Through f of x, or I guess we're saying f of t, so through f of t at t equals t1 and t equals t2. Okay. All of that is stuff that you could have done before this year. And we did do. And you did before pre-cal even. You did some average rates, I'm sure, in change in distance over change in time, all the way back to pre-algebra. Okay, so average rate, slope, but I have to have 2 times. So what's going to be different so this whole section is called rates of change, right? So what's going to be different now that we're in calculus? Instantaneous rate. That's something you saw last year for a little bit. Instantaneous rate, which tear apart the English or the word itself, the vocabulary word, instantaneous. It's rate at an instant. So how many times do I have? Just one. And since we're kind of talking about physics, let's make it t sub 0, like an initial time, but I'm not saying it's always the initial one. Just I use t1, t2 on the other page. Let's use t sub naught or t sub 0. At one time. Now, how does that give me a dilemma with what we just talked about, finding rates of change the old-fashioned way, average? If I plug in, the only time I have, am I going to have a dilemma? What do I get? But now that we're in calculus, we've been talking about limits, and even at the end of pre-calculus last year, we're not scared by that. We just think we don't know what it is yet, so keep going. We don't know what it is yet, so keep going. But how? This is literally identical function minus an identical function. How do you factor and simplify? If it's the exact same thing, first minus the second, well, we have to think about it a little bit differently. We're not going to fill in the blanks quite yet. Secant line. Secant line goes through. If I wanted to find my tangent line or my instantaneous rate, my slope at one point to a curve, or at least one point over an interval containing x sub naught, I would have to remove myself from that x. I would have to choose another x that's aside or away from the original. And as soon as I move that x, I now have a change in x that is not 0. So that will exist. But the problem is this slope the exact same as this slope? No. And more specifically, what's the relationship between these two? Who's greater? The steeper one, the tangent line, because my slope is going to be higher, more positive, right? So A, secant line isn't the tangent line, aka his slope isn't his slope, and not even that, he's much lower than, right? They're still both positive numbers, but very different. So what could I do? This will find me a number. What can I do to get my secant line closer to my tangent line?
Move it up gradually.
Move it up? Well, I'm going to move it up by choosing different points. So whatever x I chose, I'm going to come a little closer. And what's going to happen to the change or the difference between? It's going to get a little bit smaller. And I'm going to get even closer and closer and closer. Let's illustrate that fact.
Would you recommend we draw this?
I would recommend you draw this. Why is it not clicking? Oh, I think it is clicking and I just froze my computer.
Or right there. Oh, it's red.
Yeah, he's not happy. I didn't. Thanks, Bill. Great idea. So, note to self, impatience is not always a good thing.
Whoa, what?
It's opening quite a few. Nope, now he just froze.
Oh, control of
I know, because I hit him too.
Whoa.
Oh, there's a lot. Yep, there's 7. And we're back. All right, so let's go ahead and delete just a few of these. Got it. Okay. So, thank you for your patience. Quick demonstration. Old-fashioned way. Just make lots of different pictures on one slide in like PowerPoint. Okay. I have a point at which I want a rate. And the way I find a rate at a point of a position function is to find the slope. Slope of what though, Jezreel? Tangent line. It needs to skim. Like imagine that you're in like a roller coaster car, and if that like extended out into a line when you're about to like go down on Viper or something, where would that line be? It'd be skimming, right? Your car would be making contact, but if you made a line each way, that would not be hitting, etc., etc., etc. You're skimming. Okay, I want this one. Oh. But I can't get them because I can't plug into the formula. But I can find this one, right? I pick a point, I find it. You guys look at the very bottom. I can plug in, I can get a slope. Ta-da! But is that the slope of the tangent line? No. How can we make it better? Get closer. A little better. Closer. Ooh. Now, if you guys are looking at the bottom, question. It's getting closer and closer and closer. It's getting infinitesimally. Ooh. That was from like Newton or Leibniz, one of them. It's getting closer and closer. It's going to converge to, I know how to take limits. I don't have to get at the tangent line. I can approach it and I can use my logic to say, hey, what is the slope of the tangent line by looking at what the slopes of the secant lines as a removed point gets closer to the point of tangency? What's it converging to?
1. Negative 1.
Negative 1. So I can say, hey, I'm approaching and it will converge to the slope of the tangent line, which is negative 1. Okay, back to notes then. I'm going to get closer and closer and closer to my tangent line and thus converge to what the slope of the tangent line is. Let's fill in a couple of these blanks. Slope of the tangent line is the, if I need to be approaching, it must be a, right, our keyword. It's going to be the limit of the slopes of the secant lines as, is there a special way of writing the difference between two x's? Triangles. Wow. Deltas. What's going to happen to my delta x as I'm trying to make my removed point get closer and closer and closer and closer? Delta x is going to not just get smaller, go to approach 0. I can't be at 0 or else my formula wouldn't work, but I can approach. Now, how to actually solve. Are you guys still filling in?
No. Oh.
Well, I have to see my. Okay.
Whoa, magic.
How to solve? Focus. How to solve? Graphically. Whenever we do anything graphically, maybe I shouldn't say whenever. Most of the time, when we do something graphically, we're doing it approximately. We're doing it approximately. Now, I just randomly made up this curve, and I made it all pretty in period 1 with tick marks and like numbers, and I picked a point. Whatever. If I wanted you to find for me the instantaneous rate at 7, You don't know a function. So you can't figure out like removed points and then secant lines. What's the best you can do? Try to think about a line from like a roller coaster car extending out and think of, well, about where is this one? The best you could do is pretend. And be like, looks like a tangent line to me. I'm going to approximate it. How could you approximate it if you have a graph and you have a drawn tangent line? Figure out maybe where it hits something else I know besides the point of tangency. Figure out what 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then say, well, it seems to kind of hit that point, and it kind of hits that point, so I'm going to approximate. And how would I approximate it? Rise over run. Now, why can't I just always do this? Why does there have to be this whole branch of math called calculus? Why don't we just draw pictures and then approximate? Because every time we introduce error, our calculations get further and further off. There are a lot of things that depend on calculations that came from the study of calculus, or it uses the study of calculus, and if we were off by a little bit, literally, lives could be lost. So, let's come back. Think about it. Engineering, electronics, technology. Okay, come back. But we're doing the approximate. All we've got is a graph. So therefore, how could I approximately find my instantaneous rate? Or my slope of, I guess I should put it two ways. I should do slope of a tangent line. Let's make it all accurate. Or I could find like instantaneous rate. I'm giving it little like sub names that way we can know what they are. So slope of a tangent line or instantaneous rate is going to equal change in, well, not equal, approximate. Best I can do if I have a graph only. So my instantaneous rate is approximately, well, the slope I think is kind of close. But does it make sense? It's a positive and it's going up and it's not very steep, so maybe 4/7 makes sense. Graphically, it's not horrible, but is it precise? No. Algebraically. Let's take the fill-in-the-blank words that we put over here. Let's put them into math. If I am going to find the slope of the tangent line, which is the same thing as the instantaneous rate, we'll do instant, there you go. I know that it's going to be the limit, of the slopes, okay, so f of, minus f of, all over, change an x I can do. Back here, in my graph, if I knew my point of tangency, and I wanted to get to the other point I was going to pretend with and find a secant line, what could I add to the original to get to the new x value? The distance, otherwise known as the change in x. So therefore, I'm going to keep this all super general and say, start from the point of tangency in essence, add a change in x to say that you're somewhat removed, so it's not on top of each other, aka 0 over 0. Make it something a little bit removed, minus the original y. So y2 minus y1 over x2 minus x1, but generalized using the delta x as much as we can. And what's going on as my secant line gets closer, 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 closer? Delta x is approaching. We're not making him a forever. So we're not really giving him a proper name. We're just describing what he does. His proper name is for Monday. But what does he do? He finds the average rate, he finds the slope of the tangent line. How does he work? Slopes of secant lines as they approach the tangent line, as the change in x gets smaller and smaller and smaller and smaller. So how does that apply to you? Grab out your books, page 176. Sadly, this book I do not have an electronic version of, at least, well, no, I don't think there is one right now. New editions, maybe. Page 176. If you don't have a book on you, Shimmy up with your desk. Don't make it awkward. Shimmy up with your desk next to someone who does. Don't make a big deal about it. Make a big deal about it. Literally, move your desk next to someone who has a book because it's going to be so helpful to see the problems. What? We use our book in this class? I know. What are you talking for? All right. Go ahead, groan. All right, fine. Groan, 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 groan. No. Why might some people be groaning inwardly or outwardly? What do you see?
Graphs.
I was thinking words. All right, fine. Graphs are horrible. Graphs. All right, come back. Now, one quick note for homework number 10, section 3.1. I only gave you 1 or 2 evens. Why?
So we can check back.
Got it. And unlike Calc Chat, this doesn't just like randomly blah, 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 all this stuff you can write down and pretend to understand what you were doing. So it only lets you check your answers. Okay, come back. Number 2, I want you guys, or whoever is sharing the book with you, lean in so you can see the book or else go share with someone else. I want you to read number 2. Go. Let's see how horrible these words and graphs are.
Unique life segments shown in the figure. An estimated instantaneous velocity of the automobile at time equals 4t as n. Again, n t equals 8 seconds. Distance in meters 200 by 8 meters. Time in seconds 2.
Once you finish reading, go totally silent so I can tell when you're done. Once you finish reading, go totally silent so I know you're done. Okay. Question. What are you given in number 2?
Numbers and words.
You're given a graph, right?
Oh.
What has been marked on the graph? Well, first of all, hold on. What is the graph?
Automobile driving.
Over 10 seconds.
I heard automobile driving and speed and over 10 seconds. What is the graph?
The speed of an automobile.
I don't think it's speed of an automobile. What is it?
The distance traveling.
The position. I know it's a little complicated. We're just getting into this. But they said these are distances. So it's where or how far away it is at each of these times. So this is my distance. Measured in what? Distance measured in?
Meters.
Oh dear, you guys are killing me. Come on. And then my x's are seconds, so therefore I'm probably measuring time. True?
True.
Okay, so I have 2 questions before me. If you guys read all the way to the end, it said, what were they asking you to find? Estimate velocity at and at. Hold on. What is, if this is distance, how on earth can I estimate velocity?
It goes through the point 40.
Velocity is like a rate. Distance over time, it's like a slope. And if it's only at 4 seconds and then separately at 8 seconds, is it over an interval average or is it tangent line?
Tangent.
So what did they give you at 4 and at 8 to look at? Points with tangent lines. So look at them separately. First of all, just look at the one at, you can't really tell that I'm highlighting. Okay. Look at the one that goes through 4. Now, granted, mine isn't perfect, but I tried to get as close as I could this morning. At 4, look at the tangent line. That's approximately, this is an exact tangent line. I'm going to try my best to approximate what this slope is. How can you figure out slope from a graph?
It goes through 2.
Rise over run. And if I were you, I would do exactly what Jezreel did, which was say, hey, it kind of goes through 2, 0, right? So if it goes through my point of tangency, which seems to be kind of like 420, and it goes through 2, 0-ish, couldn't I find my velocity at 4 seconds to parsecs to be approximately change in y, which is 20, over change in x, which is 2? So therefore, 10 meters per second is approximately how fast you're going at 4. What did I do? Figured out a point on my tangent line as best I could. It's a graph, it's approximate, change in y over change in x. Now, what am I going to do at 8? Same thing. Can somebody look at your graph? It's better even than mine. What's the point it seems to kind of go through?
4.
4-ish? Okay. I'm not saying it's perfect. I'm not saying it's perfect. And problem is checking your answers with the book on this one. Do they have the perfect answers? Yes. So should your answers necessarily match theirs? No. But should it be close? Hopefully. Like you shouldn't have a positive when they have a negative. That's bad. Okay? Come back. So if I was to find my velocity approximately instantaneous at 8, I would figure out my rise, which seems to be about 95, anybody? 97, 96, what do you want? 95. And then change in, well, that one's easier because that one's 4. Between 8 and 4 and between 0 and something. I can say it's approximately 95 over 4. Look at us being all creative but trying to be cool. All right. Done. Graph. It's approximate. Best you can do. So many words, but was it really that hard?
Yeah. No, for this one.
Because I asked someone to find the best point, and the best one they saw was 40. Is that perfect? No. It's a graph. I have to be approximate anyway. If you could find a better point, awesome. Use it. You might be closer to the actual. Now, what if it says solve algebraically? Look at number 14 with me. What does the question ask?
Find a formula.
Hold on, where's number 14? Find a formula for the slope, and then B says, like, solve. Okay. Find a formula for the slope at a point. Didn't we just talk about how there's a formula for slope of a function at a point? Taking a, doesn't this look like practice test?
Yeah.
The limit on the practice test? Number 23? Sure was using it. You were finding the slope of a tangent line on that one. So why on earth do I expect you to be able to do this math? We basically did. It's just going to look a little funny because we have a delta x. If you don't like them, once again, make them an h. But otherwise, I can go ahead and plug them in, simplify, take my limit, and solve. So I end up with x plus delta x squared plus 3 times x plus delta x plus 2 minus, that's just my f of x plus delta x, minus f of x. Don't forget your parentheses, distribute your negatives, plus 3x plus 2 all over delta x. I cannot. So maybe just go to plugging in the formula. You cannot forget that this is a what? Write it. My ones who totally ignored me before, you better not now. So rewrite the limit. Then I plug in. I get 0 over 0. Keep going. How? I FOIL. I simplify. I combine like terms. And I end up with all kinds of stuff. Oh, that was weird. Simplifying because the nature of the beast. We saw a lot of like simplifying stuff last chapter, right? I'm almost there. If I look up top, I see every single one of them shares a delta x, which is good because finally I can get rid of my removable discontinuity. I now plug it in, and I get 2x plus 3. A is done because I have my general formula for the slopes of the tangent lines to that curve. What does B say to do? Solve for it at a specific. How do I do that?
Plug it in.
It's an x. I need an x. So therefore, and even if I didn't need an x, I still plug in. So define The slope at 2, I just say 2 times 2 plus 3 equals 7. Dun, 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 dun. Woo! We made it with 10 seconds to spare. All right, cool kids. Homework this weekend. Homework number 10, section 3-1. We beat period 1.
Yeah, we're better.
Oh, yeah.
By like 30 seconds, but we still got there. So, WQC number 2. Sorry. Read section 3-1, homework number 10. Bye, cool kids. I'll see you Monday.
Rahul, I love you.
Need the idea because the AP test is. They give you limits and they say, what are these? What are they standing for? How do you solve them? And you can't do them the limit way. You have to do them the derivative way. It is. I forgot. We'll do it Monday. Limit handouts. We'll turn it on Monday. On my lunch, we're still amazing on top of things. You are lucky I forgot.
All of it, all together.
Yeah. Homework packet in the back. Chapter 2 practice test in the back. This is supposed to be today. If you have it ready, turn it in. Otherwise, I'll take it Monday. Yes. Please tell me you don't have the meeting. Please tell me you don't have the meeting. Yes. Can I get copies? They don't get all of these.
Hey, Luca, why'd you look? Why did you look? Sorry. You're making jokes in class. Wow, man. What?
Because I wanted to see why Luca was in his class.
Oh.
Come to see Luca.
You looking back? Let's do it. I love this beer so much. Yeah, I know.
Wait, is this
Oh,
the
it's
whole
in
lesson?
there somewhere.
Yeah.
That's my ex.
It's a free calculator. Oh, you can pick up your stuff.
Is this the whole lesson?
Yep.
It's the math teacher's dream, a free calculator.
I know.
Yeah, with my name. Nice one. Not even
Last time I found it had things that the batteries and it's like